GSA Discussion Series. And I say first annual because this is something we hope to continue yearly to get some academic sort of discussions happening on campus and just give students a chance to practice and present their research in an open forum and give everybody a chance to come and give some feedback and get some feedback on your research. That's not just from your supervisor, it's helpful sometimes. I'm Brendan, I'm the current president of the Graduate Student Association, and
I'm Sidney, I'm the social media.
So, should we go on that?
I do actually.
Go ahead.
Having been to many international conferences in my area of research myself, it can be extremely intimidating to meet the experts in the world in your field and have to present your research the first time ever and then suddenly be, I don't know what I'm doing, it's hard for me to network, it's super expensive to go, I don't have the resources to get to the conferences in the first place, and so on. And we thought that this is something that presents a research opportunity at home that you're able to go and in a low pressure environment present your research, that you don't feel that you have to have it perfect the first time, and in fact, use this as a forum to take your presentation and improve it, refine it, get feedback on it, and then bring it to the next level. And pack your CV at the same time. We think it's fantastic.
It is fantastic. And I guess I'll take some time to plug some official business. If you haven't voted yet, if you're a GSA member, you should. The election's on right now. Ballots in your email inbox, and you can vote up to our annual general meeting at next Wednesday, 4 to 6 o'clock. The meeting's held at L239 at the Student Center. You can vote there as well in person. And there'll be some free pizza and beer for people who want to show up too, so spread the word, because free food is awesome. Also free beer.
And get your friends to vote as well. It's extremely important.
So,
we're spending your money all the time. You should at least have a say in it. Show up to the meeting. Have a say in it. We have to have forums to make things happen.
it's true. So,
Please show up.
We'll probably mention that a few more times in the next day or two, so you'll hear about that a bunch, but stuff you don't hear about much is research. So we'll get started. Our first presentation today is Reza Talebi with three-dimensional reconstruction of small objects by using the fringe projection method. So you ready?
Yes.
Go for it. Yeah. Flashing red button. Turn the screen on.
Do we have one of these?
No.
Good afternoon, everybody. My name is Reza, and now I'm presenting my thesis for you and hope you enjoy it. I started this research like a year ago, in a continuous way of my attraction in geographic fields. I have to work in a geographic company. So this three-dimensional reconstruction of small objects. When I say small objects, it doesn't mean that very small object. It actually practically means not very big objects, not buildings, not big statues, but regular objects they use. You can see in the museum or sculptures. So because you have this limitation with the projector wide angle, so we cannot actually scan the very big objects. So to go on, my supervisor is Dr. Julia Johnson. I'm a graduate student in the Department of Mathematics and Computer Science. Here I'm going to talk about where actually we can use 3D models and what's the demand, what's the application, what's the main reason that we should produce three-dimensional models. And the next, I'm going to just explain very briefly about classification and methods, generally about how many methods are there in 3D reconstruction of the objects, And at last, I'm going to show you some of my preliminary results, outputs, and that's it. I'm not going to go in very detail. It's not going to fit in 15 minutes at all. I'm going to talk for you for 3 hours at least, so you can really understand what's going on. It's very wide area of research. It's been there like 40 years. Lots of implementation, lots of attribution has been done on. So we can use 3D models, 3D reconstruction models in photogrammetry. We can use them in computer science, in medical science, and in so many other fields. Reverse engineering in industry, they widely use them. And at last, in animation and visualization and game industry, animation industry, we can use them. In geometric or geographic fields, you've seen them nowadays everybody. Google Earth, Google Map. They use 3D scanners in the streets. You have seen them that mainly work with interferometry, and they create some models. Here is a SAR scan image of 3D cloud points. I'll explain what cloud points are. Cloud points are a cloud of points in very simple way to explain, that has been coordinated, each point in a 3D mesh world system, and we can use them because each pixel or each point has its own coordination in 3D world. We can use them as the most precise 3D model to use in industry or geometry field. This image is a 3D model meshed according to the cloud point above. And this is the laser scan output, 3D points, as you may see, or like in real fields. They use them like LiDAR scans and these things that we use to scan big sculptures, big buildings. We can use 3D models in computer science. We can use them in pattern recognition. There is this huge notion that a 3D model of an object simply gives you more information about the object. Because of that, in point of view that we see an object, there will be extra different information representing to the viewer. So if we see an object from one angle, it doesn't mean that it also contains all the information in other angles. So if we scan that object and produce a 3D model and then reconstruct them and compare them with the objects or in our knowledge base, for sure we can get more specific results. So it's a very active field in object recognition, pattern recognition. These days they use it to just implement and go on in this way. We can use in medical sciences so widely. Nowadays people with disabilities, they have to create or build some artificial parts of body for that person. But these artificial part of body that actually should fit precisely with the body of the patient, so they should have the precise measurement of the body and the part they're gonna produce for that person. So if they can scan both the patient and the part of body they produce, they can fit them together perfectly. Or if they scan the size of the lung in a patient in a period of time, they can understand that by the differences or the changes have been made through the time with the lung, the clinician can just find out what kind of disease may have happened to them. To go on, in 3D virtual worlds, it goes without saying that it's really, really helpful. Instead of you assemble a big editing team or graphic design team to just sit by computers and just design a regular room like this. You can actually print or scan one of these objects and multiply them, and it will help. It will save lots of time. 3D scanners in widely they can be divided in active sensors or passive sensors. It's very big. I'm just going to introduce and go on. Active sensors there are sensors that have some kind of relationship or touching relationship with the object. But passive sensors, they don't touch the object in a very simple way. Like using optic laser scans, they are passive sensors. These are, for active sensors, it can provide divide the triangulation, time delay, like SAR scans, like CMCs. This is a very big field of study. Each one of them has a huge story behind it. So I just go on and based on this active and passive sensor fields, we can divide 3D modeling in 4 base systems. One of them is image-based rendering. In image-based rendering, you just take the pictures and it doesn't lead to 3D models. You should process them, and in some applications with special position or situations, you can lead to the 3D modeling, otherwise you can't. In image-based modeling, it's completely different story. They use it in LiDAR laser scans. They use these image-based rendering. They actually render the scene and scan each pixel or each element, smallest element in the scene by the methods they use. So it's widely used for big sculptures. In range-based modeling, they use active sensors. But because the active sensors are very expensive these days, they have huge limitation in real application. And we have combination of image and range modeling, which is they can combine these two and just apply it in some special field or a special problem. They can create some solutions. Okay, 3-dimensional. we can categorize these my 3D-dimensional using digital free projection. So it's a non-contact method. It's based on optical measurements, and it's based on interferometry techniques. And here is the free digital mapping. Okay, for the free digital mapping, we need a projector unit. We need an imaging unit like a regular camera, and we need a processing unit. So as you can see, comparing to the other models or other 3D scanning systems, it's very cheap, and it's in more cases it's very faster. So it contains of 4 main steps. First, we create the patterns. We create some sinusoidal patterns.
I have a class here in 5 minutes.
We booked it through Director of Services.
What?
No. It's booked through Director of Services, so no, it's not all right. Thanks.
Okay. We create and project. We create the pattern. We project them on the object. Then we calculate the phase. I'll explain what the phase is. And then we should unwrap the phase and then convert the phase to the depth information. Okay. Here we can see that we have the computer, we have the processing unit, we have the camera, and we have the projector. We create the patterns here. We project them on the object. Because these patterns has been resorted due to the topology of the object, we can actually gain our depth information due to this absorption of these patterns that has been absorbed. So you can see, this is a projector, this is the pixel on the projector, we call it the phase line. Because we know all the properties of these patterns generated or created, and we know everything about the pixel cameras or any optic properties of the cameras, when we project these two, these will just interfere in one pixel on an object. And by doing some calculation that I will explain, we can exactly understand the depth information of this pixel on that image. Okay, here is a little example. We just projected some patterns on the patterns are horizontal. They can be vertical. Here is a simple example. Here is a sculpture. Here is the wrapped face. You can see there are some discontinuities during these pre-projected patterns, and here is the unwrapped face. Okay, for face extraction, we have three main methods or approaches. We have Fourier transform, we have wavelet transform, or phase transition or phase shifting. I use phase shifting because there were numerous, too many different properties or difficulties with these two. I tried them, they all lead to failure. So to go on, for the phase transition, we create three patterns at least, and we shift these patterns as a known angle. For example, 0, minus 120, and plus 120. Because these shifted patterns have their own equations, we just want to know the phase information of these three equations. Because if we shift them during the time and we project them on the object and we take the pictures, we can solve these three unknowns with three equations, and we can gather, we can reach this equation at the last for just extracting the phase of that specific pixel in this formula, which is this one. And for the phase to depth conversion, we use triangular simulation. This is the projector, this is the center of the projector, this is the camera, and this is the center of the camera. This is the object. D is the point that we want to calculate the depth. Okay? D is the distance between the center of the projector lens and camera lens. There are just two main...
I'm sorry, folks, I have a class here. I've been teaching here since January. I mean, there's a mistake, but I need the class.
Where is Jessica?
Sorry?
Where is the person we just left the room?
I have no idea. They're gone. So they're trying to resolve, to clarify this, but I need the room.
And you're not.
I have 27 students waiting.
No.
All right. I know what to do.
Yes, please.
Okay, at least I have more time to explain everything. Okay, there are just two main points. One, as the view of the camera, this point is similar to this point. And as the view of the projector, this point is also similar to this point. And these two triangles are similar. So we can, actually, I know that you know the equation for two similar triangles. And there is another point that, because this distance is much more wide, bigger than this distance, we can get rid of this distance and just calculate this depth. In practical usage, it's not going to make a huge difference. So we can calculate the depth over the height of this point till the reference plane or the wall or whatever is behind the object. This is the system I use, just a regular camera and a regular projector. There lots of calibration specifications. I can't talk about them. There are too many. How you put the camera and the projector together. They should be parallel. The camera and projector axis should be parallel to the reference plane axis, and the camera should be fixed. You shouldn't touch the camera. If the camera moves just half a millimeter, the pixels on the picture will move 10 or 20 pixels. So you shouldn't touch the camera, and all should be calibrated. Another picture to go on. These are just some Y patterns I use. The Y patterns help us to unwrap the face easily because the number of patterns being projected on the objects are too many small. If you want to get more detail on the depths and the details of the object, you should use the smaller patterns, and you should shift them as a tree pattern. Here is I project them on the reference plane without the object. I use two objects. One is the somehow shiny sculpture. You can see there are some shiny parts here. I'll explain the outputs that in all optic systems, reflection is the main enemy of the whole system. You can't afford to make any perfect. And the other one is this is called human skull. It's a property of forensic department. As you can see, I project the patterns on the object. They have been shifted. The patterns, the wavelength is equal to the wavelength of the projector because we want to cover all the axes in the width of the projector, and it helps to unwrap the face. I can go into any more details. I use the smaller wavelengths. Here is the output for the wrapped face, and here is the output for the unwrapped face. As you can see, the unwrapped face is very good. It's very hard, and here is one of the outputs. You can see we have in the areas that we have reflections, we have artifacts here, here, and here. And another angle, we have some artifacts also in the left side of the object. I put this output because I wanted to show you if there is any slice of calibration there.
Hey, Angel.
Okay, the end of it.
Well, I guess we're done. You already kind of throw us out.
Yeah. And another output, the same thing with the skull. It's white and it's for the image. And if there's any question.
Is it possible to, take what you're doing and combine multiple versions of it? Like I use a laser scanner for archaeology, for structural building mapping. So it would seem that if you do this, which seems like 1,000,000 times cheaper, but combine multiple end results together, you would get a better overall view.
For bigger sculptures,
Yeah.
for buildings.
Yeah.
The really problem with the unwrapping phase, because the first thing is the calibration. How can you calibrate? I mean, the first thing you should have a projector that projects very precisely in a wide angle on a sculpture or the building first. Then, for the second part that you just take the pictures, it should, I mean, if it moves just 1,000 times of 1 millimeter, you can't unwrap them. If you can unwrap them and fix them together, it won't work. It actually, I never seen that anybody just apply this on the sculpture, because the main thing happens is that you should calibrate the system very precisely. It's like 50% of the whole project or whole system. If there is any kind of movement or any kind of, if your projector is just half a millimeter in front of your camera or vice versa. In your model, you have a big difference in the height, and you can't just do anything about them. And also on graphing things. Search on any other.
The colors you're getting, is that because of reduced speed of light?
What colors?
The artifact colors.
You mean this thing?
Yes.
This thing here? Yeah.
Well, on the
There-
skull you got a bit green. Is that because the light is slow?
Oh, the skull gets a little bit green.
Yeah.
Okay, no, that's not. Oh,
Or is that
like
just
3
colors?
hours. No,
Oh,
because when you project the patterns with the projector, the patterns are actually contains of RGB colors, and they project the projector LDP processor. They just shoot these patterns, combine them, and shoot them on an object with a specific speed, actually. So when you want to take the picture, your shutter speed should be reduced in order that if your shutter speed is like, for example, 6,400, it may catch one of those lights. It may catch green, red, or blue, one of those RGB lights. So when you want to take the picture, you should reduce the shutter speed, not in the way that you make the whole object white, because it also gains more color, more light. Because when it wants to take the picture, it goes blink, and it stays for 1 second, and then close the shutter. You should find all these things. It's another problem with the calibration. You should all just fix all these little details to get a good results. That's because of that, the green or things that you can see. Yeah. Any other question? No? Thank you very much. Thank you for your time.
So what's the situation?
We're allowed to stay. Yay.
So did they move them to a different classroom?
Yeah, then we have to see to it for crisis averting.
No, I'm not.
Next